These procedures are recommended to be put in place. Why? Just to ensure that the holes are drilled very safely and safe discharge of explosive energy. The very first point is that preparation of drill site and marking of drill holes using different color for different types of the holes. Pegging of depth indicators for showing required depth of drill holes at varying surface conditions. And just to ensure more accuracy in drilling, using a GPS system is recommended. Here in the photograph, which I have told you now just, practices is being done. Drill holes are being marked using different colors. It's being done in India, it's being practiced. Drill depth indicator has been pegged, showing the required depth. While drilling front row, is from my experience I am telling you, maximum care should be exercised for marking because there is a chance of drill rig toppling. So it should be so oriented and it should be so marked so that it can reduce the risk of drill rod rig toppling. Drilling should not be carried out in a hole where any part of it is considered within an unacceptable distance from a hole containing explosives. This normally, as a part of our SOP, we used to practice a 30-meter safety distance for drilling from the hole containing the explosives. Now I will come to the safety aspects of blast design parameters. In blasting, that is the main activity amid all mining cycle of operations. So, ensuring of safe execution of it is very much required, is of utmost importance. So, what are the recommended do's are? Recommended do's are, the very first point is blast plan preparation. Blast plan should be meticulous. Meticulously we have to plan the blast plan beforehand charging commences. And it should detail the methods and the manner by which it will comply with the requirements, ensuring safety and security at the working place. It should be done, it should be planned beforehand of the charging operation starts. Latest software, as you all know, JK SimBlast, ShotBlast, can be used to tailor, blast plan can be tailor-made using this. Documentation of various parameters. We do a lot of jobs in this field, but simply we don't document it. In most of the mines I see, they are very much, they are very poor in documentation part. But we do suggest documentation of various blast parameters should be done religiously. And for that, a mine-specific format should be devised. That format should ensure safety and security. Next point, daily pre-blast morning meeting. This is not done in the, I have not seen in any of the Indian mines is being done, but pre-blast morning meeting and the mine pit is very much required. Why? Every mine has got their own schedule of mark generation plan. It's annual, is monthly, and is weekly. Just by back calculating it, you have to decide the number of blasts you have to take per day. And that will help you to eliminate lots of hazards, and that will help you to ease out the blast planning also. Daily post-blast evening meeting also is required to line up various post-blast activities as well as to decide and freeze next day blast, so that drill coordinator can plan according to drilling activities as per blast requirement. Blasting in charge should make himself available throughout the blasting operations, just to ensure the safe execution of the entire blast operations. And selection of explosive also plays an important role. As you all know that earlier ANFO used to play a major role in big size blast. Now with the increase of security concern, we have changed over to SME. And same holds true with the accessories also. What happened? Next, no? Thank you. Now I will suggest some special safety precautions. These are, we used to address this in our common parley, is all weather safety precautions. These should be followed unfailingly and religiously during blasting operations. Utilization of safety equipment must be made mandatory. It has to be made mandatory. And in most of the cases we see, there is a general tendency not to comply with the PPE requirement, but it has to be made mandatory with the commitment of the management. So personal protective equipment means, we have given some examples of personal protective equipment. These are very much must. Retarding clothing, gloves, goggles, coppering, anti-static footwear, cotton jackets, etc. Only competent persons should be allowed and authorized to handle and use of explosives in regard to ensuring safety and security at workplace. Because nowadays, in the pretext of safety, blasting is considered to be a highly skilled sector. So we propose that the handling and charging operations during blasting should be handled by mining engineers. And any activities proximity to the face should not be taken up, which can generate heat or sparks. These include smoking, naked flames, or operation of machinery. Unauthorized personnel and machinery, those who are not involved in the blasting operations, needs to be removed at a safe distance from the area. Movement of the mobile equipment near blast places, only the permitted vehicle should be allowed under the special spotter. Separate parking place positively should be given to the light maintenance vehicle. They should not be allowed to enter into the charge space. I have shown in the photograph separate parking zone near the charging faces, barricading before the charging, and blast site with the caretaking spotter. Display of signposts. Charging areas should be suitably marked with the appropriate warning signs. In case of sleeping phase, in most of the cases this is not done, but sleeping phase, what we suggest, suitable warning signs and lighting arrangement should be there, so that the approaching man and machinery can easily see and identify the charge spaces. And the communication devices like mobile, walkie-talkie should not be allowed to direct enter into these charge spaces. Precaution during usage of bulk explosives in charging. In charging part of the, during charging of the holes, lot of risks are involved. But here also we have to take some precautionary measures, and by adopting it, we can reduce lot of risk involved in it. While is it? Always we suggest to develop a site-specific, mine-specific SOP. And devising of SOP will reduce, let me tell you, is very simple. We do it, but we don't do it, we don't follow it. Just using that SOP that can reduce blast-induced hazards to a minimum. And these SOPs, how it can be developed? It can be developed in 3 parts. Suppose precautions prior to be charging. What are the points to be covered prior to charging? Blast limits first should be delineated. Then comes check measurement of the holes. Then one has to ensure the completion of drillings and redrilling. And then before charging operation priming operation start, we must shift away all machines from the blast site. And this is to be ensured. I have shown in some of the photographs that these practices are being followed. BMD is very important. BMD vehicle in its positioning, prior to charging, it has to be taken care of. In nowadays, I have not found out any mine where there is a particular system of BMD vehicle checking for entry into the mine. There has to be, we always propose just to have own fitness test and checking system for every mine. They should have their own, depending, it has to be site specific, mine specific. It can be fortnightly, it can be monthly also. And every loaded VMD vehicle, there should be a separate parking place in the mines, pitted. And in the photograph, you can see, is a separate safe parking place. All BMD vehicles are loaded, but separate parking place have been given for them. Another is that during charging operation, we suggest to position the BMD vehicle along the parallel to the drill holes, because this will ensure the direct eye contact between the operator and the hole measuring supervisor. Because this is one of the reasons I have seen lot of blast problems occur due to overcharging. Arey hole bhar gaya. But how it can happen? Only just because there is no proper communication in between the operator, BMD operator, and the charge and in the measuring supervisor. During precautions during charging, this is all know, all precautions during charging like earthing of BMD vehicles, removal of ignition key, and then tire stoppers should be a part of the SOPs. Yes, another thing I will suggest, special care must be taken while charging the watery holes. You see, this is the keep, watery hole charging. Funnel must be used, be made mandatory while charging watery holes down the hole, because this will ensure quality SME charging down the hole, in the watery holes. Post-charging activities. Post-charging activities means stemming. That is also another important part of the blasting operation we should take care of. We recommend to use plastic funnels and stone aggregates. These are better to be used for stemming operations, so better confinement of explosive energy and containment of rocks. Another thing should be taken care of, leftover explosive mixtures in the hose pipe and inside the hopper of BMD vehicle should not carried away from the blast site, should not be carried away in the blast site. Once connection is completed, visual checking and face inspection should be done by blasting officer. In case of electronic blasting, yes, blast face testing is to be done by the blasting engineer himself. It's not like another person will come. He himself will inspect that. There are some pre-blast and post-blast measures also, apart from what I have discussed now. Making them the part of the SOP will definitely reduce the hazards involved in the blasting. What are that? During blasting, blasting coordinator should always be in contact with the security team for guard postings. And after evacuation, ensuring evacuation of all persons lying within the 500-meter radius of blast area and getting all clearances, then siren should be put into the operation. After blasting, after conducting all proposed blasting and dispersing of blast fumes, blast face must be inspected by the respective face in charge and clearance will be given for successful completion of the blast. Then long siren should be run for once only for all clear message, allowing entering of the people for next shift people for operation. So, the practices which I have deliberated now is not like that. These are only paper talk. So these are being followed practically in Indian mines and some of the big open cast mines, wherein productivity has been overshot. At the same time, to practicing the highest standards of safety norms. So, in conclusion, we can infer like that the safety proposition as we recommended are very much clear, realistic and in sync with the achievement of stiff production target with safe blasting operations. Definitely adoption of the safe blasting practices coupled with the latest technology will give us more confidence in handling, transport and usage of huge quantity of explosives. This will definitely rebut the slogan, even though safety and production appear to be paradox, that they can coexist. Thank you.
Thank you, Mr. Mandal, for your lucid presentation. The do's and don'ts and the SOP that you've talked about, if everyone follows that, I'm sure it's going to go a long way in enhancing safety. And I hope IOCL follows the safe practices that you've shown in your presentation. Thank you once again. Well, next in line is TNT, RDX, HMX. They are the backbone of military and defense explosives. There are very few institutes, factories who actually make HMX, RDX, and TNT. In defense, we've got just TBRL, Chandigarh, and HEMRL who make HMX. In India, in the industrial explosive sector, we have Solar, who's making HMX. They've also gone in for TNT. It's only ammunition factory Karki which makes TNT. RDX, Premier is making only for their captive consumption. So, manufacturing these products, defense products, is a tough challenge. And ensuring safety during the manufacture is even more challenging. And today we have a person whom we can actually call an expert. He's done his master's in chemical engineering in 1981 from Royal Institute of Technology, Stockholm, Sweden, and PhD in computational chemistry in 1989 from Louisiana State University, USA. He has worked with Bofor's explosives manufacturing unit from 1982 to 2012. Currently, he's working as Senior General Manager with Solar Industries India Limited and handling a project on developing and starting a process for HMX and RDX manufacturing. He's Dr. Per Schoberg. A big round of applause for him, please.
Thank you, Mr. Sri Sanjoysen. Very nice introduction. Dear colleagues, this picture here is taken a couple of weeks ago from a hill at the center of the Solar's defense site, about 1 hour's driving from here. The upper building is a 3-storage mounted building where we will do filling of ammunition. And I'm talking really hardcore defense products here. We're talking about large caliber gun ammunition, torpedoes, bombs for the Army, the Navy, and the Air Force. And the method for filling the ammunition is called melt cast. This building will consume, or in this building we'll be handling hopefully very large amounts of high explosives. I'm talking about 100, maybe thousands of tons per year. And of course, when you set up this type of plants, safety is number one when you do layout, design of equipment, and you have to understand the risks handling this kind of explosives or large quantities when you do the design. And that is what this presentation is about, and that is why Solar are interested in this topic. Just give you the scope, what is melt cast for you who are not I know most of you are not from the defense business, so melt cast might be a new term for you, but it's very simple. It's what you do, you melt the explosive and pour it through a specially designed hole in the ammunition. It's like pouring water to a glass. So the principle is very simple. What you need then is an explosive that you can melt in a safe manner. And that is more difficult to find. But it was already found 120 years ago, and that is TNT. And it's still used, and it has been used, it's the most used military explosive just because of this property, that you can, the melting point is quite low, it's 80 degrees only, but it's stable up to 250. So that means it's a big window where you can handle melted TNT safely. And so far, 120 years after it was invented, it's still the only major used explosive for this type of application. Since the problem with TNT is that, but there are other high explosives that have higher performance than TNT, and that is RDX and HMX. But they cannot be used because be used in the same way as TNT because you cannot melt them. Because if you melt them, they will decompose, and that would be very dangerous. It's impossible to handle melted RDX and TNT. So what you do instead is that you mix RDX and HMX with TNT, and then when you melt that mix, you get a suspension. And I know in your business, you know what suspension is. You have solids suspended in a liquid, and the liquid is TNT. So you have two compositions. They have many names, but the most used name is composition B is RDX and TNT, and octol, it's HMX and TNT. So that is the scope of this plant in terms of explosives. So the most obvious risk, the first risk at least, that you start to think about when you're going to do this is that you have to work at elevated temperature. And we know all explosives are, they cannot take any temperature. There are some limits how much high temperature, what temperature they can take. They start to decompose, and especially TNT, these type of explosives used here, they will start to decompose at the catalytic. That means you can get a slow reaction will convert to a fast reaction very fast at certain temperatures or certain times. But I will not go through this, but in my presentation, in the paper that we have, that is in your proceeding, you have a lot of references to the literature, published data on the stability of this explosive. And my conclusion from reading that carefully is that working as long as you are below 120 degrees and don't keep it at that temperature for more than 24 hours, you will be safe. And that is with a good margin. And it's also a good margin for the process. You don't need 24 hours to do this operation. You will need maybe the cycle time is 3, 4, 5 hours at the most. And 120 is way above the melting point of TNT. So that is, you need some rules anyway. So that is the rule that we have for this plant. 120, 24 hours. We have something to stick to. And we will keep the temperature, well, let me tell you a little about the reactor. It's still on the sketchboard, as you can see, when I made this presentation, but now it's actually built and mounted in the building. Anyway, it is a simple reactor. It's a cylindric reactor with an agitator to keep the suspension, to keep the product in suspension, and also to keep the heat transfer better. And it's jacketed for controlling the temperature. It's jacketed on the mantle and on the bottom. And the safest way is to use hot water circulation. You can use steam directly, of course, but hot water is safer. It's safer to control that the temperature never gets above 120. And to be on the short side, you can also put a safety valve onto a bar that will make it hardly impossible to increase the temperature with more than 120. This is a very traditional way to control the temperature, and it will work. That is. What also you can do is to have an interlock. The agitator needs a motor, electric motor, flame-proof motor, of course. And if that stops, that means that the inside temperature of the reactor, the plate here, will be hotter. It will become the same temperature as the circulation, which is 120, and that is necessary to keep that for a long time. So what you can do, you can interlock the circulation with the agitation. That means if agitation fails, hot water circulation will stop. And that is very safe to do with the PLC. Very simple. It takes just a few seconds to program that. And then what is more important is to use some kind of raw material classification or clarification before you use it. And one of the most best method I like most is VTS, is vacuum thermal stability. It's a method that will, because what I said this explosive will be stable at 120, but that is as long as they are pure, right? They should not contain impurities that could, for example, be catalyzed for decomposition. But you can do that with, run VTS on all raw material that you get from your supplier. And before you before you put it in the plant, you make this test. If it doesn't pass, you don't use it. Another risk is if we get a fire, of any reason, you can have a fire from the outside, you can have you can never eliminate the risk of a fire, even if you control the temperature, but it could be other reason for fire. What is the risk for detonation? A fire you probably could survive, you can run out from the building. But if you have a detonation, there is no chance to survive in this building. It's because we are handling large amounts of explosives. You have some good, a good guide here, that is TNT or RDX, or the composition that I'm talking about here will not will not go from deflagration to detonation as long as the pressure is below 300 bars, which is very high and well above the design of the reactor, of course. But the temperature can increase very fast, and I think the best countermeasure for this is to have a bursting disk. A bursting disk opens and ventilates the reactor much faster than, for example, a safety valve. And so you put a bursting disk, you can have a set point of 1 bar. There is no reason that you should have more than 1 bar, so let it open then. And it should be a bursting disk that opens without loose fragments, so you don't get any loose fragments down to the reactor, because that is then you create another risk. Another thing, this is another risk for fire to detonation is the bottom valve. Normally you will use a bore valve. That is the most common valve for this type of application. I made a drawing here of a bore valve. It's very simplified, as you can see. A bore valve doesn't look like that, but anyway, it shows the principle that I want to make. That if the bore valve is closed, you will have a confined space, right? That could be filled with explosive, and that is explosive. That is a very big hand grenade, for sure. And if you have a fire, this will certainly build up a big pressure here, and it will work like a bomb. It will create a detonation that can spread into the reactor. And so, my suggestion is to use some other type of valves, not the ball valve, not here. What about the explosive vapor? You will use TNT at elevated temperature. So of course it will evaporate. How dangerous is TNT vapor? Is it flammable, for example? When you talk about the flammable liquid, what you want to know is what is the percentage, the lowest level of ignition. That is what you want to know, and it is not published for TNT. But you can do some smart guesses, and you can use, for example, something called Suzuki empirical formula, where you can get the lowest level energy by using this equation. Put Hc is the heat of combustion for TNT, and then you get 30,000 ppm, 3%. And you can also use the stoichiometric concentration in air. You are familiar with that, I know, and that is very simple. You can calculate that for TNT, and that is, then you arrive to 20,000 ppm, which is 2%. And then you compare that with the volatility of TNT at 90 degrees, which is the process temperature, which is only 2 ppm. So we will never reach that level we will never reach that concentration where this could be a flammable gas. So that is not a risk. What could be a risk is that when you run this for a longer time, this reactor will be ventilated. You need to ventilate it because you want to avoid TNT coming into the room. So you will have ventilation with a fan. And if you calculate, if you have, for example, a batch size of 600 kg and you run three kettles in the plant and you run shift, 3 shifts or something, 3 shifts, you will evaporate 100 kg per year. And that TNT will not go out. It will condensate somewhere in the pipe, for sure, because the pipe is cold and TNT will condensate at if temperature is less than 80. Even in Nagpur it will condensate. So how do we avoid that? Like here, you have risk for TNT condensation. Well, it's very difficult to avoid it. What you can do is you have a good distribution of flanges, so you can do maintenance. You can open the pipeline easily, and there is no area or pipe that is difficult to reach with some cleaning action, like, for example, a solvent or something. So it should be well flanged, many flanges. Of course, you always have, when you work with explosive, you always have this risk with mechanical impact and friction. The explosive we are using here are certainly sensitive for impact. It is, as RDX, TNT, HMX are in the same, at least like between 3 and 5 joules in the fall hammer. So it's not like primary explosive, but it's significant. Especially TNT also, because TNT, it gets more sensitive when it's melted, and it's going to be melted in this reactor. And also the sensitivity increase when the temperature increase. So that is a risk for this plant. So what you don't want, this table here, it shows the fall hammer sensitivity of TNT with how it varies. You cannot see that here, but yeah, you can. How it varies with temperature. And so you can see that it is drastically more sensitive at 120 degrees than at the melting point, 90, 80. So what you don't want any hard objects. You don't want someone to drop the flashlight into the reactor or a wrench or something, or anything, stones or anything, because it will hit the impeller, and then it will, the chance for detonation is very big if that happens. So you will, of course, one action is, of course, to have a sieve on all the inlets that will take any large object that, or it should be any object that is bigger than the clearance between the agitator and the wall of the reactor. You need to also have a stable clearance between the wall and the reactor. You should not have a agitator swaying. If the agitator hits the wall, it will certainly detonate. And you also want a soft-seated bottom valve. I mean, you should have a gasket, of course. No metal-to-metal friction, that is obvious. It should also have slow action. There is no reason to open it fast. So you have low pressure on the actuator, so it opens slowly and closes slowly. That will reduce the friction very much. And you have on the, and then you have the shaft entrance to the reactor has a strong mechanical seal, because you have a lot of torque on the agitator, so it leaves a strong mechanical force that is friction and spark free. But that you can buy on the market. There are companies that make this. They are very expensive though, but necessary. Another thing when you do this, the product comes like TNT and octal. It comes in drums like this, and it's a powder, right? Granules. And the powder, powder is not only powder. Powder also contains dust, right? Fine particles that has been created during the process at the supplier. And that will, of course, be airborne whenever you do anything. When you empty this ton into your process equipment, you will get a cloud of dust. And how dangerous is the dust then? That is, of course, a risk, since it's an explosive. You can, in the literature, you can find some written about risk of TNT and dust explosion. But it is found, there is one literature I found, they have a maximum pressure and the pressure rise for TNT in a dust explosion. It has these numbers. It doesn't say anything, but when you put it in they have a scale. They put TNT as a number 1 in the scale from 0 to 3, where 3 is the 0 is non-explosive and 3 is very, very strong explosion. So it is weak. And also, if you look at the U.S. Bureau of Mines have also published TNT, and it's actually less severe than coal dust. So how ignitable is it then? That's another question. Now we know it's the action of an explosion, but how ignitable is it? Well, that is also published. Minimal spark energy for TNT is 50 to 75 megajoule, and composition B is 30 to 40. So that is, it is low, but not that low. It is not. It's energy that we can handle. You cannot get the spark energy from an operator, for example. On a hot surface, it will not ignite until the temperature is about 200 degrees. And there is no reason, nothing is 200 degrees in the plant. The hottest thing is the hot water pipes. They are only 120 degrees. And all equipment are classified T6, which means that they are not hotter than 60 degrees. And also, another thing, how high concentration do you need to have an explosion? Well, for TNT, it has been showed in a Hartmann tube test that has been published. You have to have 70 grams per cubic meter. And in Bureau of Mines, you have to have 170 grams per cubic meter. That is an enormous amount of dust. If you really have that dust, you will not see your hand in front of you. And in an operation like this, it is very unlikely to get more than 2 grams per cubic meter. So dust explosion is a low risk. Doesn't mean that you should allow dust, of course. You should have good ventilation, but it's not a big risk here. What about when it settles? Dust will settle. It will be airborne for some seconds, and then it will settle. And it will settle on the floor, it will settle on the equipment, it will settle everything that is horizontal. And there you have some interesting information. Actually, it only takes 1 millimeter for dust to sustain a burning reaction. So very little dust will burn if it catch fire, of course. And if the layer gets more than 2 to 4 millimeter, it will go to explosion or a detonation or explosion. It will not detonate because it will never reach that pressure in a room. But anyway, you will have a deflagration and explosion. So, I mean, dust is absolutely a risk. I'm talking explosive dust now, of course. And then you have the spark sensitivity. The spark sensitivity is like 30 millijoule. It's not, a person can only generate 20 millijoule when it's very, very dry. Normally, a person only generates 1 to 2 millijoule. What is more critical, I haven't talked about that, you will probably use acetone in this plant for cleaning. And acetone is much more ignitable than any other material in this plant. So you should think about that when you design the electrostatic rules. So here are the final actions for settled dust. You keep the plant clean from dust, that doesn't mean that you clean it, it means that you clean it regularly, but it also means when you do the design of the plant, you should avoid having hidden surfaces, no dark corners. Avoid horizontal surfaces as much as possible. Of course, the floor will be horizontal, you have to have a floor, but make the floor should be visible. You should not have to, take away things to see if something is on the floor. You should see it by taking a slow walk through the floor. You should see all floor areas easily. So you can easily flush it. And I think that is very important. And you apply T6 for the equipment. Minimize. Anti-static regime, you will have an anti-static regime. You can look that up in NFPA. You have your own rules here in India also, but this is National Fire Protection Agency agent in US. They have very good rules that are easy to understand, and you have semiconductor rules here. That means, yes, and that was my final slide. Thank you. Thank you for, thank the organizer for this, for inviting me. It's a great honor for me to, we have national meetings in Sweden also for mining and explosives. And you have maybe 20 to 30 people. But even if Sweden is, we have a lot of explosive history, but here you can see how big India is in this business. It's a privilege to be here. Thank you.
Thanks, Dr. Per, for sharing your knowledge and experience. The biggest challenge for you is how to upgrade the safety systems in the existing plants, because there are no manufacturers in our country who manufacture TNT, HMX, or RDX. So that's the biggest challenge for you. And in our country, we have the petroleum rules, and then we have the ATEX directives. And the conditions in India are different from what you have in Sweden. So it's a real big challenge for you. And in fact, the High Energy Materials Society, they are working on how to replace TNT, RDX, and HMX with extremely insensitive detonating substance. That's what Dr. Agarwal was talking about in the first technical session. So in fact, if you go by the UN classification 1.5 and 1.6, defense, they do not have any explosives which falls under this category. So the international explosive community, they are working towards moving toward much greener and much safer explosives. So there are explosives like TATB, NTO, which can replace RDX, HMX, TNT, and which can fall into the category of 1.5, 1.6, but that's a long journey. Anyway, thanks for sharing your experience and knowledge with us. A big round of applause for Dr. Pearl. Any manufacturing activity generates a lot of waste. And waste disposal is a big nuisance and very dangerous. And there have been instances where accidents have taken place in the industry, in the defense sector also. Now that the industrial sector is manufacturing propellants, there have been accidents while destroying composite propellants in Ordnance Factory at Archie. There have been accidents in Ordnance Factory, Kamaria, Jabalpur. There have been accidents in Orica, IL, Gomia while destroying explosives. And we have an expert, a real expert, who's been associated with the explosives industry. He's a 1978 batch postgraduate in chemistry from Osmania University. He joined the R&D team of then Ideal Chemicals Limited, presently Ideal Explosives Limited, a unit of GOCL Corporation Limited, Hyderabad. He's working in the same company for the last 38 years. His area of interest is in the study and computation of explosive properties through tests, software programs associated in the in-house development of such programs. Currently, he's working as General Manager R&D Explosives with Ideal Explosives Limited. He is none other than Mr. Vidyasagar Narla. Please.
Good afternoon, dignitaries. Greetings to all. In fact, this is a paper. It is not one paper. Two papers are made into one due to time constraint. My friend, Mr. Sitarama Swamy, was supposed to deliver the second paper. Now I would be doing both the papers. So there was mix-up of slides. So first paper goes and the second paper would have been done by him. Now it goes now. Basically, this is a compilation of information and our understanding on the subject and also our experiences on the subject. Every industry, every company manufactures, whoever is manufacturing explosives, they will manufacture explosives and also there will be generation of waste for various reasons. Basically, these are all hazardous substances, and while their usage, these explosives generate noise, light, sound, shock, gas volume, and all other things. So basically, these are hazardous in nature, and the purpose of these explosives is to break the rock and to move the rock. But our industry makes these substances which are hazardous, but they are made into a very safe substances with respect to handling and transportation. Nonetheless, even with all these things, the waste will generate at various stages. In other slides, how it will come will explain. So yes, waste. It is whatever waste is generating, it may cause hazard to the environment and people. So people and environment need to be protected, and the focus is given how to protect these things, or I would say is rather safe disposal of these waste materials. Basically, these papers are, first paper is aimed for safe disposal of ammonium nitrate based explosives, which are slurry and emulsions in a large quantities being made by our companies. The second part goes accessories, blasting accessories we call detonators, detonating cord, shock tube, and other related things including PET and TNT, RDX, HMX, so on, so on. In fact, that is a bit complicated as far as disposal is concerned, whereas disposal of the so-called class 2 explosives, ammonium nitrate based, is a bit easy compared to those things, because basically these are not that hazardous compared to blasting accessories. Whatever class 2 explosives that are being made by us, our industry, essentially it consists of water. Those days, explosives were there without any water, particularly NG-based explosive. Disposal, destruction would have been tougher. But in case of water-based explosives, water is an essential constituent apart from ammonium nitrate and other things. These things we made them very insensitive compared to NG explosives. So any waste, it is easy to generate by way of blasting. But not all, detonation, what I would to say is detonation is the most preferred way of destroying. But all facilities, all places, it is not possible. It is possible only at the user industry, that is mines. So the best way of safe disposal of these explosives consisting of water, ammonium nitrate is by way of burning only. It has some disadvantages because water being an essential ingredient, the burning also becomes difficult, and but we have to do, that is the most safest way. The other thing is dissolution and dilution are also methods where, in dissolution and dilution means mostly water is used, particularly slurry explosives where, unlike emulsion, they can be disintegrated in the water. Again, there also, once all water-soluble ingredients are, once they go into water, water-insoluble materials are they will be there, and those will be filtered, and they will be again sent for burning. And whatever water-soluble portion essentially containing oxidizers has to be treated again, adopting proper procedures. Only thing is that in this, you are disintegrating the explosive and handling materials which are not hazardous. But nonetheless, again, the procedure lies like burning and treatment of water-soluble, the liquid, and whatever pollution checks we have to do, pollution controls for water treatment we have to do. So best way is to do the burning. The other thing also involves using desensitization. Again, desensitization also generates a lot of wastewater that again has to be disposed of. Only thing is, in dissolution and desensitization, we make the explosive less hazardous and do the treatments. In case of first two things, as such explosive is disposed of. The most preferred way is by way of burning. So in case of burning, again, three things are essential. The site selection, site preparation, and how a site has to be, and what materials are required. Most of the information is there in the detailed paper, but the site has to be, main thing is site point of view, it has to be far away from regular vegetation or habitation, buildings, where activities are there, main roads, railways, and it has to be a bit away. And in addition to that, the site has to have approval of PESO in our country, and the site has to be well guarded, well fenced, and if necessary, firefighting equipment also have to be provided there, along with CCTV cameras, to have close observation of things, whatever are going on. Then site has to be, basically the site has to be barren land, without any stones, without any larger ingredients, because during burning, these stones can be propelled and they can become very hazardous flying objects. We have to consider burning is taken very lightly. Burning of explosive, disposal of explosive is taken very lightly. But it is nothing less than a manufacturing process. The way we take care of safety precautions and other things while manufacturing, similar amount of efforts or precautions we have to do. It is nothing less than a manufacture. Destruction is also, is a hazardous process. We have to take all possible precautions. So the site also has to be that way. Sand particles or stone, bigger stones, or even any objects which can be propelled, they should not be there on the ground. The ground can be of barren soil, as I told, or it can be made of fire-resistant bricks, compact clay, or otherwise concrete, but the concrete has to be without any fissures. Otherwise, an explosive can penetrate into the fissures and can cause havoc. And the materials needed are generally wood, paperboard, or even wood carvings, which are combustible substances basically. The other thing is we require, because water is an essential ingredient for these emulsion and slurries, we need to have combustible liquids which should have high flash point as well as very low volatility. Means they should boil at very high temperatures, and they should not. Preferable things are kerosene and diesel oil. So kerosene and diesel oil are the preferred carbonaceous substances or combustible substances used for burning these explosive substances. And when we go to the site, when one takes up burning operation or disposal operation, one should see that it is free of any hot spots, because one gang or one crew must have already done burning there, and definitely there would be hot spots of the previous burn. So one should ensure that there are no free burns. Or in case when hot sun is there, during very summer days, certain places there could be hot spots, and such things also can cause hazardous. So we should ensure that the burning place is cold, it's not hot, not of any hot spots, and only authorized quantity of explosive only has to be subjected. Whatever specified quantity is there, that much quantity only we have to take, and we should see that detonators and explosives should not be clubbed. Detonator should not be there. If we have to ensure that there is no detonator, no other substance which is other than class 2 explosive is present. Otherwise, there can be havoc. As far as burning is concerned, there is other thing is that confinement. We have to avoid the confinement. To avoid the confinement, the slurry or emulsion has to be laid as a thin layer. The thin layer can be about 20 mm, 30 mm, or maximum 50 mm. So, the explosive has to be laid into layer, or one cartridge, say 25 mm, 32 mm dia cartridge, one cartridge as a layer, one cartridge as a layer. Like that, 50 kg quantity of explosive can be made as a one lot. Then, maximum we can go for 3 lots. One lot generally should have about 50 kg, and thickness of the cartridge, explosive should not be more than 20 centimeter, 20 mm or 50 mm maximum. Then, the explosive has to be spread on wood shavings or carbonaceous matter, cardboard and other things. Then, after spreading, again it has to be spread with kerosene or diesel oil, and it should be lit. And once it is lit, the operator has to go away to a safer place, and the preferred way of lighting is against the wind. Against the wind gives controlled burning. Otherwise, there can be accidents also. After about 2 hours, one has to come back to check the explosive, and any unburnt explosive should not be handled, because unburnt explosive remains in very hot condition. The these substances are very, very sensitive when they are hot, so we should allow them to become cool. Then only they have to be again tried for destruction by way of burning, adopting all the precautions. Then again, ashes, whatever are generated, to be collected and disposed of according to the environmental permits or in accordance with the practices. Details and quantities have to be properly recorded. Very important thing is, site should be guarded properly, as we have discussed. Firefighting equipment has to be deployed. Compatible explosives only have to be burned. That means detonator-like things should not be clubbed. Then weather conditions have to be considered. 2 heavy winds, we should not undertake any burning. And never, explosive should not be buried as a way of disposal, or thrown into rivers, or other way of contaminating the water bodies. That is not a method of disposal. Incompatible substances like sulfur and chlorates should not be burned together. Similarly, ammonium nitrate and chlorate should not be burnt together, because under hot condition, there can be, the mixture can be hazardous. One should never add, see, already we started, one has lighted the fire. Neither explosive nor kerosene or diesel should be added. That causes havoc. Then during heavy winds, this should not be taken up. From this part onwards, my friend Mr. Sitarama Swami should have taken up, but I am continuing. So we discussed most of the points. What to destroy: slurry, detonators, detonating fuses, pentolite boosters, RDX, HMX generally that we generate. And why the rejections are coming? Rejections are not fit for usage, unsafe for handling and transportation, spillages. Or when to destroy: the physical damage, human errors, shelf life expiry. These are other causes. Where to destroy? We have already discussed specified, authorized, open space, underwater, in the pits. Underwater is applicable for few things, not for all types of explosives. Who can destroy? Personnel authorized by PESO under the supervision of experienced with appropriate equipment. How to destroy? Burning, detonation, blasting, desensitization. These are the four methods generally available. See, as far as detonators is concerned, detonators best way is by way of blasting. I think most of we people are destroying detonators by way of blasting only, but not in larger quantities, very small quantities. And one way of burning, one way of destruction by burning is also reported, but that requires armored furnace. By keeping armored furnace, by deploying armored furnace, detonators can also be burnt. There is also one chemical methods reported, but that is applicable only for aluminum detonators, where aluminum will be dissolved in dilute hydrochloric acid. The remnants will be destroyed, and again the acid will be taken for treatment. It's a bit laborious, so best way is by way of blasting, and small quantities are there. Then the same thing is applicable for shock tube detonators and electronic detonators and other things. Then as far as detonating fuse is concerned, the best way is by way of burning or by detonation in small quantities. When we are doing by way of detonation, knots and other, even in burning also, detonator should not have any knots. Detonator should not be burnt when it is on the reel. It has to be taken out. It has to be spread. That is, we should avoid confinement. Then the other things which we handle and generate are safety fuse, shock tubes, and delay composition and delay materials, black gunpowder and other things. These have to be disposed of only by way of burning. They cannot be subjected to detonation or any other methods. In case of black powder, it can be disposed of by dissolving ingredients in the water. And again, the water, whatever ingredients it has in it, it has to be disposed of again by way of proper methods. Insoluble portion again has to be destroyed by way of burning. So overall, gunpowder or delay composition has to be destroyed by way of burning, the most preferred way. The other things our industry handles is PETN. In case of PETN also, various methods are reported. The best way is burning, or chemical methods are there, applicable for small quantities, or even some contamination in pipelines and reactors, chemical methods are deployed. In case of TNT also, again it is open burning, even chemical methods are also applicable. It's a very exhaustive paper. Because of time constraints, I'm just glancing through the contents. And cast boosters also, same way PETN and TNT, as by best thing is by way of burning. Then RDX and HMX. RDX and HMX also best way is by burning them in open fire. And there are some incineration techniques. For that, specially made incinerators are deployed. In India, we are not using those incinerators. But in abroad, I have come to know that there are specially made incinerators where these things are destroyed. But it involves, again, only small quantities, not larger quantities. The other thing is stephinic acid that we handle. Stephinic acid also by way of burning and also by chemical method. In chemical method, active groups are reduced, or active groups are deactivated, and the resultant things are handled carefully. The other thing, nitrocellulose, that is also by way of open burning. Pardon? Nitrocellulose is also by way of burning, and chemical methods are also there, and incineration is also one method. Then lead azide. Lead azide is by treatment with, chemical treatment is the only best way. There are also some reports, disposal of lead azide and lead stiffnate in the form of water slurry in wet condition. But generally, I think most of the people are doing by chemical method only. because it's very hazardous. Even ASA, lead stiffenate, lead azide way of in wet condition also reported to be hazardous. And there is another electrolytic method is there for lead azide. I think in our country we are not adopting this. Same lead stiffenate. Then contaminated and packing materials also, we should practice all precautions as applicable, what contamination they have. Thanks.
Thanks, Mr. Vidyasagar, for your extensive and exhaustive presentation. You've probably covered destruction of all the products except for probably composite propellants and ammunition. And that's probably the biggest challenge for the industry now, that the industry is switching over to defense explosives. What happens if a batch is rejected by defense, a batch of ammunition? Do we have the expertise? It's a challenge not only for the industry, it's a challenge for PESO too. And in your presentation, you were mentioning something about destruction of TNT and incinerators. I have really my reservations on that. Incidents have happened with explosives in confinement. There is every possibility of the explosives going off. There have been instances of destruction of NG explosives when the entire NG explosives has burnt off. Practically nothing is left except for ashes. And when the officers have gone to see the site after half an hour of burning, at one particular spot there was just some bit of smoke which was coming out. And when they approached the site where the smoke was coming out, an explosion took place and 2 officers were injured in that. So we really cannot be complacent in destroying explosives. And regarding the compatibility, what you were talking about, there is a government notification which says that sulfur and potassium chloride, they should not be mixed together. So the legislations, everything is in place. Only we have to practice it and see that the lives are secure and we destroy the explosives in a very, very safe manner. Thank you once again, Mr. Vidyasagar, for your presentation. Well, mining is something which I really don't understand. But we have the next presentation on unlocking iron ore by controlling environment effects using blasting systems. There is a system called Monte Carlo model. So for describing this, we have an eminent speaker. He's done his BTech in mining. He's been working in various fields of blasting technologies, mainly in open cut coal, metal mines and quarries. He has specialization in mineral recovery, machine productivity, improvement, environmental blasting, and many other complex blasting operations. He has published many technical papers in Indian and international journals. Currently, he's working as Technical Service Manager with Orica. He is Mr. Rajendra Konidina. Please.
Thank you, Chairman, for the introduction. Good afternoon to everyone. I come from the area where I use explosives. My manufacturing guys manufacture the explosives, but explosives does have big safety concerns that the user face. So apart from pre-planned detonation or premature blast, there are other effects of blasting, especially on the environment. The proven 3 nuisance out of blasting are vibration, blast-induced vibration on the nearby structures. Second one is basically air blast, which is the noise which rattles your windows. And the third one is the fumes. So fumes is also one of the biggest issue. And last one, I would correct that. Last one, another one is a fly rock. So these are the 4 major nuisances generated when we conduct a blast in mines. So based on this, research has started way back in 1980, mainly by US government, US Bureau of Mines. In 1980, they were given with a task to identify different root causes for what is actually leading down to the generation of the vibration. So they have come up with few empirical formulas. At that time, the explosive products available to them were detonating cords, ATMAX, non-electric detonators, and then they had NG-based explosives, high-end explosives. So our theoretical models which we have got in prediction of vibration and air blast are dated back to 1980, which we generally currently use in our country. However, from 1980 to 2016, we have made lots of advances in manufacturing technology. So we have come up with lots of new products. We have got more control over the blasting process with the precise initiating systems and more safer explosives and more high energy explosives in the mining field. So my paper basically deals with the environmental controls, which talks about vibration control from blasting, and second one is the air blast. Honestly speaking, we have developed, all the scientists in the world, like we have developed, we could manage to model vibration control blasting, but air blast, no. Nobody could crack that nut till now. Nobody knows what happens before the blast with respect to air blast. Nobody knows about it. So Orica is working with Curtin University, Cambridge University in developing those numerical models. We have a long way to go. There are so many factors when we talk about air blast. So today we stick our topic to environmentals, which are majorly air blast, which I would say because of some tools that has reduced. And we have done lots of work on vibration, which we could manage to control it. So I wanted to share a case study, which we have done in India, which used lots of tools in predicting the blast before actually predicting the vibrations before actually firing the shot. So this is one of the iron ore mine we have got in India. So the agenda which I wanted to cover is like situation of the mine, and what were the observations and what we have done in controlling the vibrations, and what were the results like, and where we can go ahead in the future with respect to these technologies and how we can replicate in the other mines. And most of the customers are using it, premium ones, but there's a long way to go before we get these tools into the mines, each and every mine around India. So it's one of the biggest iron ore mine we have got in India. It has got a massive hard ore. In terms of iron ore, 66.5% grade, which is a very high grade. India has got very good reserves of iron ore, at par with any other country in terms of grade. This mine has got huge expansion plans. So they had like, the situation is like they had 7 hills. So iron ore generally occurs in the hilly terrain, and we do not need to muck lots of waste. We can directly get into the ore and dig it directly. So they had 7 hills. One of the hill has got hard ore. So for if you understand steel making process, hard ore is a very important ingredient for blast furnace. It takes the load of the coke and iron ore. So it's very important you blend your ore with a hard and soft ore. So they got exhausted with the hard ore in the rest of the mine. So they had to excavate that one hill. And the challenge with that hill is it was surrounded by a village. So the village range is from around 150 to 600 depending on the area of the hill where you are blasting. So it was very crucial for them to expand their operations in that hill. But they couldn't blast in that hill for the last, I would say, 2 years because there was an incident of fly rock and a huge vibration issue. So they stopped blasting operations for 2 years. They couldn't mine there, and their requirement for hard ore has forced them to start their operations. So they've approached Orica if we can help them out with the tools we have got in terms of explosives, modeling and other things. So we've started working with them. And the limit we fixed for ourselves was like, it says like the vibration is measured in peak particle velocity per second, so millimeter per second. So we have put it as 5 millimeter per second. However, like internally we wanted to make a blast such that villagers doesn't even feel there was a blast. That was an agenda which we have taken for ourselves. So moving on, so what we have done. So if you see vibration, vibration has got many components which control the whole thing. It has got geology in it. It has got geostructural things. It has got maximum charge per delay, delayed accuracy, blast design, and the spacing between the point of interest and the whole blast. So it's a complex process. Blasting itself is a very complex process. When you talk about vibration, it becomes more complex. So what we have done is we wanted to understand the geology of the rock. So we conducted signature shots, which gives us the geology, structures, and any cavities and all those things which give us the whole idea. And then determine the site constants. Site constants depend on the area where you're firing, and the sonic velocity. Sonic velocities is when you fire the shot, you generate lots of P waves, primary waves in the ground, which are contributing for the vibration on the structures. So we need to understand at what velocities they are traveling. And then establish a predictive model, Monte Carlo. So I'm pretty sure all the graduates here would have gone through the Monte Carlo iteration processes. So it's a similar sort of a model, but with some complexities involved in it. And then finally predict the vibration before the blast and confidently say with 95% confidence, before the blast I can tell like my PPV would be 3 millimeter per second. I can put my hand on the heart and say it would be 3 millimeter per second. So that is the confidence level we need to have before we conduct this sort of blast. So we have done lots of monitoring stations. Monitors like this is the plan of the pit. So we have established lots of monitoring stations. Monitoring stations is one of the key aspect for measuring vibration. In India, there's a bad practice like people do not give lots of importance to the measurement systems and how to be measured. So there's a huge awareness we need to put in the industry, like a measurement system, correctly measuring, reporting correct data would help us in improving ourselves rather than reporting the wrong data. So if you see the setup on the right side of the photograph, this one should move as according to, if the ground moves, this should move. If you just place it on the ground moves, because of the ground movement, it resonates. It gives a wrong reading. So what we have to do is, we have to have a cylindrical concrete block, which goes at least, I would say, a feet inside the ground with a bolt in it. And you have to bolt that monitor onto it. So then only you get the correct vibrations. Otherwise, you won't get the correct vibrations. You would get resonance, which would not give any scientific use. So it's just, we are doing a compliance. If you want to do something good, we have to have good measurement systems and good practices. So we have got similar sort of measurement systems at different places. We have got so many monitors, and then we found the contours. And finally, we managed to get the site constants for that site. So which a PPV equation everybody have studied, every mining engineer knows. It's a very outdated equation, but still it helps in getting us the site constants, attenuation constant. That means waves get attenuated at a particular interval at some rate, and amplitude constant, so the amplitudes also get attenuated. P-wave velocities, which is very important, at the rate at which the velocities are traveling, which contribute to the vibration. And finally, ground frequencies. So frequency and PPV, peak particle velocity, are very much interlinked. If you want to have higher PPV, you need to generate more frequency. Suppose a simple example I can tell you, like if you have got speed breakers, when you drive a car, if you have got speed breakers, a big hump on the road, you would typically slow down your car and feel the whole hump. And if you have got small speed breakers of very high frequency, you just rush through that. You don't reduce your car speed. So that is basically high frequency. A high hump with a big width is basically a low frequency. Similarly, if we produce this low frequency waves, people will feel that vibration. If you produce high frequency waves, people will not feel it. That's how the whole mechanism works. So you need to generate high frequencies. So again, perfect, we have got all the inputs. The inputs for this is seed waves. Seed waves is basically which has got signature of that rock with all the structures and everything. And then we have got site constants, then the velocities. If you have got a blast patch of 200 meters, I've got a point of interest here. That hole is, like my point of interest is 100 meters here. That hole is 200 meters from this, and this hole is 100 meters from this. So there's a huge space difference. So that wave reaching here and this wave reaching here is going to be different. So it has to be like you need to have that modeling work done so that when is that wave reaching, when is this wave reaching, and then put it to overlap, reinforce the waves, and then understand the whole thing. So it's a human being cannot do it. We need to have a computer with good modeling iteration systems. So, and finally, everything is a tool. And last comes, the main thing is the brain of the human being. If you know how to design the blast using all these tools, then we can get the best result out of it. So these are all tools. It's you who can design the blast perfectly and then give the results as per the requirement. So finally, we put all these systems into the Monte Carlo vibration model, which gives us the frequency and the PPV predicted. So these are the tools which we have used. We have used electronics for the precise control. This gives us the more control over the blast. And the designing tools, which is Shot Plus for Auricus. And then we have got SideCAD, which is a vibration analysis software, which gives us the frequencies and everything. And then Monte Carlo prediction model, which is the heart of the whole brain behind this. So every part of this is very, very important. And if we can't have this, we can't do a vibration control. I can't put my hand on my heart and say I can give you this result. So as typically every model has to be calibrated. Even my sister works for ISRO and they also calibrate their rocket launching systems and everything. So every model has to be calibrated. So what we have done is we have done small blasts and tried to calibrate that with our Monte Carlo model. So if you see the blue line is actual vibration we are getting, and the red line is the predicted vibration of my Monte Carlo. So typically the blue line is lower than the red line in terms of PPV. The only reason is because the model assumes when you break the rock, the vibrations doesn't pass through it. But the model assumes the rock is not broken and the vibrations are passing through it. So then what we do is we adjust that factor by introducing screening parameters and the damaging parameters to do that model. So we give that model the damaging parameters and then we calibrate it. So that's how we calibrate the model. So finally, we could manage to calibrate the model. We started with 20 holes in that patch, and then we slowly moved up to 150 holes. Right now we are doing 150 holes. I've just taken a few shots. So if you see that red color and the blue color, it's almost same. So my model is predicting 100% correct. I can put my hand on my heart and say to my customer, sir, be rest assured, you'll get the right results. So that's what we have been getting with this model, which is phenomenal. And this paper was also was presented in Russia last year, and everybody was stunned to see this model. Like, it's very difficult to get this sort of a model. Orica has tried at different places. There are errors here and there, 90%, but this model is perfectly working, still now. But we have to keep on working on this model. When you move to the new area, you have to develop new model. So that's how the whole thing works. And not only the vibration, if you see the traces, so this is the trace, blast trace. This is the predicted trace of my Monte Carlo, and this is the actual trace. If you see, it's almost similar. Not only the PPV they are giving, it is also giving me the confidence on the blast waveforms. So which I can accurately say, okay, yes, my model is working correct and it is thinking correct, and I can rely on that model with higher confidence, which is perfect. And the second, this is the PPV thing, which is okay. But the second thing which we tried is, like, we want to have higher frequencies on the ground because we can tolerate the higher PPVs. So we designed for the higher frequencies. So this graph typically says what is the energy dissipated in the blast less than 10 hertz of the frequency. So initially we thought like it's 10 hertz, less than 10 hertz, 90% of the energy was dissipated. But we thought we will push that to 40 hertz and we will see if we can get that. But unfortunately, the ground was not supporting higher frequencies. The rock should be hard, competent, intact rock so that we can propagate higher frequencies to the larger distances. But that rock was not supporting it, so that's evidently shown in the next graph. Even if we tried for the new blast, 86% of it was less than 10 hertz. So which says, like, I couldn't manage to get the higher frequencies, but still we could manage to get the overall PPV, which is less than 5 hertz millimeter per second. So overall, we could manage to get vibrations much, much below than what we have set for the target. So we were around 1 millimeter per second, so no villagers used to feel it. And one more biggest psychological effect for villagers is the air blast. Nobody feels the vibrations. Everybody feels like my windows are rattling, my vessels are falling off from my shelves. So this is the effect which happens on the villagers. So because of electronic detonators we used for this program, because no explosive is there on the surface with the electronics, and we try to take in the front holes and try to control the horizontal and vertical pistons, so we could manage to decrease the overall air overpressure. So that's by chance we got it because of the electronics, not because of any designing or anything. So finally, to the conclusion, we could manage to get a very good model. We are continuously getting the results perfectly, and we have started with 20 holes. Now we are firing 150 holes, 200 holes. Honestly speaking, the number of holes is not at all dependent, the PPV is not at all dependent on the number of holes you fire. You can fire any number of holes, but still you can control your PPVs. That's what industry should learn, and even the regulators from DGMS side and everybody. We should work together and get new rules in the system where it says like, it's not the quantity, it's actually the precision of the blast and the control of the blast which gives you the things. Finally, I just want to show you one of the video. This blast was loaded in 4 days. It is the super control blast. This blast had a highway. This was in Hunter Valley operations, Rio Tinto's operation in Australia. It has a highway, super highway at 60 meters, and it had electrical lines, the high tension lines, which supply electricity to Sydney at 150 meters. And the whole blast was around 1,500 tons, which was loaded in 4 days using 3 MMU trucks. Only 3 MMU trucks in 4 days. And this had 1,700 holes, and you can see how controlled the blast is.
Preparing to fire in 5, 4, 3, 2, 1, fire.
So that was 1,700, 1,500 tons, 1,700 holes, and 2.2 kilometers patch. So that's the scale of operation gives us the opportunity and all these things. Thank you very much for your time.
Thanks, Rajendran, for your wonderful presentation. Though I don't understand mining, but I was spellbound. And this is the second time I'm seeing the video. I'm still fascinated. Thanks for your wonderful presentation. And we've talked about technology, we've talked about everything. End of the day, it's the people who work. And most of the accidents which take place, it's primarily because of human failure, human behavior, that accidents take place. Now we have an expert who's done his graduation in chemical engineering. He had also done diploma in production management. He has 39 years of experience in the field of explosives. His area of interest are manufacturing and HSE. He had worked with IBP and ICI Orica in different capacities. Presently, he is working as general manager, technical and HSE with Caltech Energies. He's popularly known as YN Upadhyay. Please.
Respected Chairman, dignitaries, PESO officials, ladies and gentlemen. I would like to straight away go to the subject because of the paucity of time that you have. I can see people are looking towards exit. So, straight to the subject. Let us accept that we in explosive industry are different from other industries. We deal with energetic materials and pack high energy in our product meant for construction or destruction. We wonder and feel shocked when some incident happens in an explosive industry. Our reaction is very transient, and the dust settles down soon. The event is managed, formal investigation held, and some so-called corrective measures are undertaken to satisfy ourselves and the regulators. This is a hard fact of the industry. Fallacy of investigation. In the process of investigation, first casualty could be the truth behind the accident and the loss of learning from the incident. More often than not, we ignore, omit the human behavioral aspects behind the accident. Some investigators may look into the technical aspects, hardware and process related of the incident, and try to address the technical slacks only. Most of the time it happens. Quality of investigation matters a lot. This is very important. In order to elaborate, let us check out the accident triangle. Accident happens due to loss of control in hardware. In hardware, we can say design, maintenance, etc. Process, method of operation, parameters, sequence, and controls. And lastly, human behavior, which is the most important, and behind all of this, how we behave while operating and managing. Let us understand the human behavioral complexity. While a safe plant, hardware can be designed, installed, a safe procedure can be written and adopted, but most complex is the human behavior, since all of us are different from each other, unlike machines of the same make and model, because our models are different. We are all different from each other, unique. Our behavior can be better explained by ABC model. Let's check it out. See, we call it activators. We get instructions, guidelines, SOPs are there. They activate our behavior towards a particular pattern of behavior. But what happens is consequences registered in our mind of a particular behavior, that becomes much more important. While activators guide our behavior, consequence perceived, recorded in our memory motivates the behavior. Our action will depend on the relative strength of the two. You see, this is the activated, this side, activators and consequences. In consequences, what is the soon, certain, and significant outcome of the behavior or action becomes more important, and it outweighs the activators. Otherwise, despite all the SOPs, despite all the good instructions and procedures, why accidents happen? It's the human behavior which is behind it. Very simple example, we don't take poison because we know the result is certain, soon and significant, we'll die. But we smoke even after knowing its impact on health. There are numerous examples which can be given. We'll give some examples from the explosive industry without any reference. Let's take it only for academic discussion. One highly experienced operator alerts the sequence of P and CNA addition in PET and nitration. Nitration lead blows off, and one casualty because of the fume inhalation. Acidic PETN left overnight on the acid filter due to vacuum pump failure. The material decomposes, deflagrates, the nitration building collapses. Another incident, PETN plant was shut down to carry out modifications to increase PETN capacity. The modification was given to a contract engineer. One of the welders brought in a 1-inch pipe stored in a separate place and started cutting it with an acetylene torch. When there was a sudden explosion, result was frightful, as 4 people were killed on the spot, 4 died on the way to the hospital, 9 were injured by flying fragments of the pipe. The pipe had been used on the PETN plant and contained residual 500 grams of PETN in the entire pipe. The man taking it was trying to smuggle out the brass valve attached to it. Very small thing, but so many people were killed just because of his decision to cut it. During waste detonator destruction, a very well-trained and knowledgeable operator lights the safety fuse holding the free end of it in his hand, and he lights the match. He thought that he will just drop it and escape. He would have been doing it for long, but that day was not his. So the embers fell into the open end of the cap, and there was an explosion in which he was very seriously injured. The above examples of human behavioral peculiarity causing nasty accidents clearly indicate that despite training and knowledge, the individual's perception of the consequences were different, gained through own previous experience, and were outweighing guidance given to him. Now, let us talk of how to modify the behavior of the people. It is possible to modify human behavior towards safer side in our industry, which is facing the challenge of complexity in human behavior causing accidents. Let us discuss some of the tools which are time-proven in tricking people to safe behavior. Like increase positive consequences of the safe behavior. People should know that if I behave it this way, there are good consequences. Like if you pat him publicly, recognize him, reward him, it's known that people get enthused to, motivated to follow the activator's guidance. Increase negative consequences of unsafe behavior, like penalty, reprimand. Why in Singapore nobody litters? Because the penalty is heavy, the consequence is known. Decrease positive consequences of unsafe behavior. Discourage glorification and acceptance of wrong practices. Walking past an unsafe act behavior automatically becomes acceptable. Because if you walk past an unsafe behavior by a person or an operator, he takes it as the standard, and that becomes your acceptance. So discourage it, decrease the positive consequences. If you just go past, he takes it as an approval. Decrease negative consequences of safe behavior. Reducing the inconvenience in use of PPEs. Typically, in the use of PPEs, tools, if there is inconvenience attached to it, people will try to avoid it. Why we do not wear helmets? We don't wear helmets because it is inconvenient to use it. We don't wear helmets because the consequence is known, there is nothing going to happen. No penalty, nobody is going to catch. So 100 times even if there is a penalty, 100 times he will go, and once he will be caught. He can take that risk. Another way is strengthening training and toolbox talks with active participation of employees, managers, and supervisors. Many organizations have this system, and they are successful. Most organizations have this for namesake, but the perception about consequences registered in their mind can be altered. Repeated recall of previous incidents in similar operations can be powerful. These are all behavior modifiers. Another one which I myself used in my capacity in C function in Orica, Gomia people would be knowing it. This is a comprehensive behavioral-based safety program called Total Safety Culture. I experimented it in Philippines also when I was there for 5 years. What it is, let us check.